Hi. So in today's lecture, we're going to talk about finding the electric field for continuous charge distributions. So this lecture talks about finding the electric field from the expression of the electric field, not from Gauss's law. Okay, so we're directly integrating continuous charge distributions in this lecture. So in order to do that, I want to remind you of what we've already covered, which is how to find the electric field from point charges. Remember that the electric field from a point charge Q at some distance from the point charge R, right? So you're at a point of interest. That expression is the field is equal to the Coulomb constant, 8.99 times 10 to the ninth, which is shown here in this lecture as either K or K sub E, okay? 8.99 times 10 to the ninth in SI units times the point charge value in coulombs Q divided by the distance from the point to the point charge R squared. And then r hat is the unit vector that points in the direction of the field. Remember that electric fields from positive point charges point outward, radially outward, and that from negative point charges they point radially inward towards the charge. Okay? Now, if you have multiple point charges and you want to know the electric field at a specific location, then what you do is a vector sum from all of the point charges at the point in question. And so that becomes the summation, the Coulomb constant times the sum over all the point charges, Qi over Ri squared times Ri hat, where I here is the index of the charge. So why is this useful? Why am I reviewing this? Well, if you have a continuous charge distribution, then one way to look at it is you can consider that continuous charge distribution to be just made up of a whole bunch of little point charges. Now in this picture, I've drawn the little point charges as cubes, right? But if it's got a spherical symmetry, you might have a different vision of what your little charge element looks like. Or a line charge, it might look like a little slice, so on and so forth, okay? So depending on the shape, you've got these little differential elements of charge. And then if you consider each one of those to be a point charge, then it's just the same thing. You're doing a vector sum from all these little differential point charges of the point in question, and you're summing over all of those, right? So let's call our little differential charge element delta little q, right? And that's our little chunk of charge. And you're dividing your total uniform charge into these chunks. And then you're going to calculate the electric field due to just one element at a point P, and then you're going to sum over all those elements. Well, if you shrink your delta q's so that they're small enough, you take the limit as delta q approaches 0, then this vector summation becomes an integral. And that's what we're going to be doing in this lecture. The electric field is going to equal to the Coulomb constant times the integral of dq over r squared times r hat. Okay, so that's it. That's the whole idea. That's the theory. But you can see here that this might be a little awkward because you're integrating over a charge. But if you picture it in your head, all those charges, those little volume element charges, are going to be at a different distance from your point in question. So your dq is what you're integrating over, but the distance r changes, right? So how do you handle integrating over a charge when the spatial coordinate is also changing? How do you handle that? Well, the way that we're handling it is we define what's known as a charge density, okay? And the charge density expressions allow us to express our dq's in terms of the spatial coordinate. Let me explain a little further. We've got three basic types of charge densities that we're going to work with. We've got volume charge densities, surface charge densities, and linear charge densities, okay? So our volume charge density, which I'll symbolize with the Greek letter rho, is going to be our charge divided by our volume. Now, this could be a uniform charge density like I've talked about here, but it could also be a charge density that changes spatially. In that case, you're not going to have a constant or a number for your charge density, but instead, you're going to have an algebraic expression. But for the rest of this lecture, let me focus on the simplest thing first, which is when you have a uniform density of charge in your shape, okay? So if that's the case, then what you would do is you would find rho, your volume charge density, by taking your total charge. I'll distinguish the total charges from the little elements by calling the total charge big Q and the little elements little q's, okay? So we've got our total charge big Q divided by our total volume, whatever that might be for whatever shape you're looking at, right? So rho is equal to big Q over big V. and that's our volume charge density, and it would have units of coulombs per cubic meter. Okay, so that's one thing, and it's useful for spheres and cubes and big cylinders and all kinds of shapes. Now, you might have a shape that you could consider to be two-dimensional. If you have a two-dimensional shape, then you have a charge distributed over an area. In that case, it would be simpler to use a surface charge density, right? Now, a surface charge density is usually symbolized in most textbooks by sigma, the Greek letter sigma. And sigma here would be the total charge, big Q, divided by the area over which that charge is distributed. And the units for that would be coulombs per square meter. And then finally, you might have a linear charge density, and that's when a charge is distributed along a line. In that case, we use the Greek letter lambda usually to symbolize a linear charge density, and lambda is big Q divided by the length of probably a wire, right? Let's face it. That would have units of coulombs per meter, all right? So linear charge densities, that totally makes sense in electricity and magnetism, right? Because we deal with wires all the time. And you can consider something to be a wire if you're far enough away that the thickness of the wire doesn't really impact your results very much. If you get too close to it, though, it starts to look like a big looming cylinder or maybe a box, then you want to switch over to your volume charge density. So it's just whatever geometry best describes your shape at the distance that you are from that shape. Okay. So how do we convert these charge densities into our dQs? All right. Well, if you think about your charge density as being your charge divided by your volume or your area or your length, right? Then you can rewrite dQ in terms of your charge density times the volume, area, or length element. So that's what we're going to do. For a volume charge element, you would have dQ is equal to your charge density rho times your differential volume element dV. If you're in three-dimensional coordinates Cartesian system, for example, dV would be dx times dy times dz. All right, so that would be the simplest. Now, if you have a certain surface charge density, then your dq would be sigma times dA, okay? So here, sigma, remember, is your total charge divided by your area. dA in Cartesian coordinates might be, for example, dx times dy, all right? For the length element, dq would be lambda times dl, okay? So if you're in, yet again, Cartesian coordinate system, and let's say that your wire stretches along the x-axis, then you might have lambda times dx for dq. So it just changes depending on how your charge is oriented. Now, yet again, this still works if the charge density is non-uniform, but in those cases, your rho, sigma, and lambda will not be a constant, right? But instead some sort of algebraic expression that depends on your spatial coordinate in some way. And that would allow you to vary the density so that it's denser in some places and not as dense in others. All right, let's do an example problem here, finding the electric field from a circular ring, okay? An example really is worth a million words, although it might take me a million words to explain this one. Okay, so let's say that our charge shape here is a ring. We're not going to worry about the thickness of that ring, so we're just going to worry about its length, right, and its shape. And we're a distance x away from the center of that ring. And we're walking out perpendicular to the plane of the ring, some distance x, and trying to figure out what the electric field is there. Okay, so in other words, we're finding the electric field on the axis of a uniformly charged ring. Okay, so let's break this down. What do you do to find the electric field from a system of point charges? All right, well, step number one is to always draw at the point that you're trying to find the electric field what the electric field vector looks like. So here we're still doing that, right? So we're drawing our electric field vector from a little segment of our charge, which we call dq here at the top of the ring. Okay, if you do that, then you're going to have the electric field point along the line that connects dq to the point in question, which is labeled here as P. That line that connects it is this dashed line here, R, right? So R is the distance from dq to the point in question, P. Now you can see that since this is a positively charged ring, the electric field from that positive charge would point directly away from each one of my dq's. So here, I've got a DE vector drawn. And DE is the electric field due to DQ, which is here at the top of the ring in gray. All right, so there we have it. All right, now here's where a little bit of thinking comes in. We do want the total electric field from this uniformly charged ring, right? So let's think about what we're going to need. Your electric field from this DQ has two components. A component that points along the x-axis, which we've called DEX, and a component that points perpendicular to the x-axis, which we've called DE perp. As you walk around the ring, DE perp could have both y and z components depending on where you're at. So we just call it DE perp to be kind of generic. All right, now let's think about this. If you were to take the point opposite from DQ on the other side of the ring, what direction would that electric field vector DE point there? Okay, well, let's even do it. Let's insert a shape and draw that. So here's what it would look like. It would point away from that point in question along the ring. So you can imagine it connecting DQ here to point P and pointing away, right? And that's how it would point. Now, it still has a component along the x-axis that's parallel to the one that we've drawn for DQ at the top of the ring. So that doesn't cancel out. But it would also have a perpendicular component, wouldn't it? And that perpendicular component from the corresponding point on the opposite side of the ring would point opposite to the direction of DE perp. In other words, it would be equal but opposite to DE perp. And if you did a vector sum of all the perpendicular components there, from the one at the top and the one at the bottom, it would sum to 0. Now, argue this in your head. For every point on the ring, there's a corresponding point on the opposite side that cancels out the perpendicular DE perp. Okay? If you make that argument inside your head, you can see that all the DE perps are going to do a vector sum to 0. And the only thing that's left of the total electric field would be DEX, right? And then you're going to integrate that all the way around the ring. And all the DE perps, if you did the integration for all those DE perps, those would go to 0. Okay? Now, you can prove this if you want. You can solve for what DE perp is, and then you can perform the integration as you walk around the circle and show that it is 0. I'm not going to do that in this lecture, okay? But you could do it. I'm going to instead concentrate on the x component and solve for the total x component because I know the DE perps go to 0. All right? Okay, so let's do DEX. We're going to integrate all the x components of the electric fields from all the DQs all the way around the ring. When we integrate those, we'll get our total electric field at the point P, which will point in the x direction away from the ring's center. All right, so let's solve for DEX. Remember that for a point charge, the magnitude of the electric field is kq over r squared, right? So remember, our steps for point charges were step number 1, draw yourself a picture, right? Would indicate the electric field vectors. Step number 2, find the magnitudes, right? Okay, so here we're finding the magnitude of our DEX. So our DEX is k dq over r squared, and then I also have to find just the x component of that, right? So I'm going to multiply that times cosine of theta. So that's the logic here. Okay, so k dq over r squared cosine theta. What's theta here? All right. So what I've done in this picture is you've got a right triangle formed, and the legs of that right triangle are the radius of the ring A, right? The center of the ring to the point P, that's the distance x. And then the hypotenuse of our right triangle is r, right, which is the distance from DQ to the point in question. So that's r. Okay, so I defined this angle theta right here, okay? And by symmetry, opposite angles, right, it would also be the angle in between DE, this orange vector here, and DEX, okay? So that would also be that angle. This theta equals this theta here between DEX and DE. Okay, so to find DEX, I just take the total magnitude of DE and I multiply it times cosine theta, right? Because cosine is adjacent over the hypotenuse. So that cosine of theta via similar triangles is also equal to x over r. And I'll plug that in a minute. I just wanted to show you here on the diagram while our thoughts are fresh. Now, what charge density would I use for this problem? Okay, I've got dq here, but I need to write it in terms of a charge density so that I can integrate over my spatial coordinate instead of a charge. So which one would I use? Well, in this case, I've got a ring, okay? So this looks like a wire that's been around on itself. If it looks like a wire, you're most likely going to use a linear charge density, so that's what we're going to use here. Now the linear charge density, we use lambda to symbolize it, and it would be the total charge of the ring, which I'll call big Q, divided by the length of the wire. The length of the wire is the circumference of the circle, which is 2 pi a. So that's our charge density in this case. Okay, so we're defining various variables. I hope that's clear. Now, how are we going to plug this in? Okay, so we need to write our dq in terms of our charge density lambda times our dl, right? And dl is just the little segment of our wire. Now this dl, depending on the problem, could be a straight wire, right? So it might be along the x-axis and you'll call it dx. But in this case, it's not a straight wire, is it? It's wrapped around in a circle, okay? So in this case, our dl is going to be an arc length, a little differential arc length of our circle. In introductory physics courses, we often use S to symbolize the arc length, don't we? Okay? And the arc length, S, is going to be equal to the radius of our circle times our change in angle, right? So we often write S equals R theta in our introductory physics classes. Well, that's what I'm going to do here, right? So dq is equal to lambda times ds, where ds is the little differential arc length that I'm working with. Now our differential arc length, ds, is going to be the radius of our circle, which is a in this case, times our angle. Now I've already used theta, okay? I've already used theta, so I'm going to use a different angle symbol, so I picked phi here, okay? Or phi. So here I've got lambda times our radius a times our differential angle, which I call d phi. Okay, so that's our dq, lambda a d phi. If you need to think about that for a minute, go ahead and pause the video and do so. But it comes from the equation for arc length, where the arc length s is equal to the radius of the circle times the angle that is subtended, which in this case is d phi. Okay, now that I've got my dq written out, then I can write out my full expression for dex. My dex would be equal to k dq over r squared times cosine of theta, okay? So in this case, my k is there, my dq is a lambda a d phi, right? And then we're dividing by r squared, and then we're multiplying times cosine of theta. And cosine of theta was x over r. So that full expression for dx here, dex, is then k lambda a d phi over r squared times x over r, which gives you kx lambda a d phi over r cubed. Okay? Hope that's clear. Pause it if you need a sec. All right, moving on. R is the hypotenuse of the triangle, okay? And so r I can write as the square root of x squared plus a squared, okay, via the Pythagorean theorem, okay? So I can plug that in if I want to. R here, though, is unchanging, right? If I take my distance from the center of my ring to the point in question, P, I'm going to say that's fixed, right? X is fixed, A is fixed. What's changing is my angle as I walk around, but I've got the same triangle all the way as I walk around, right? X is the same, A is the same, and R is the same, even as I swing all the way around that triangle. So the only thing that's changing here is phi, right? The angle, phi. Okay, so if I wanted to, here's what I would do. I would write down my EX, my total electric field in the x direction, is the sum of all my little DEX's, which changes to an integral of DEX. And then I'm going to write my expression for DEX inside that integral. So I've got the integral of kx lambda a d phi over r cubed. Okay? Now, what's varying is my angle, d phi. How does it vary? Well, if I call my angle phi 0 at the top of the circle, and then I swing all the way around, what's going to happen is phi is going to change. It's going to vary from 0 to 2 pi, right? It's going to go from 0 to 360 degrees. It's going to come all the way around back to where it started. And 360 degrees is 2 pi, right? So I'm going to write that. I'm going to integrate from 0 to 2 pi kx lambda a d phi over r cubed. What's changing is d phi. Okay, that's my setup. Now, going to the next, right? I'm going to perform this integral. Everything except the d phi here is a constant. X doesn't change, a doesn't change, lambda is a constant, k is a constant, r is a constant. I can pull all of those things outside of my integral, and I just end up with the integral of d phi, right? If I do that, then my answer is phi. And I evaluate phi from 0 to 2 pi. I get 2 pi minus 0, and it becomes 2 pi. So my integral of ex is kx lambda a times 2 pi over r cubed. Right? If you need to think about that for a second, go ahead and pause the video and do so. Now remember how we defined our charge density lambda. Lambda was equal to our total charge, big Q, divided by 2 pi a in this case, because it was a linear charge density. So I can sub that in if I want to, because then I have lambda times 2 pi a here, right? In this expression right here, lambda times 2 pi a. Well, that is my total charge Q. So I plugged in for that. I've got kx over r cubed Q. And therefore, my total electric field is E is equal to kx q over r cubed in the x direction, or x hat, or I hat if you prefer. Okay? So that's the deal. I hope that makes sense. Okay? And if it doesn't, you're welcome to ask me questions in class, and I'll see you around.